All right, we are back with the second activity in lesson 16 of Unit 7, greatest common factor. Okay, so very important to understand what greatest common factor means. We have an example. The greatest common factor of 30 and 18 is 6. So based off of that, what do you think the term greatest common factor means? Well, let's think about what we know about 6 in relation to 30 and 18. Well, we know that 6 can divide 30, right? Okay, you can do 30 divided by 6, which would give you 5. Okay. There are some other numbers that can divide 30 as well, right? So we can divide 30 by 2, for example. There we can divide it by 10. We can divide it by 3. Okay. So there's a few different things we can divide 30 by, and 6 is one of them. 6, however, can also divide 18. All right, so when you think about that, 6 can go into 18 three times, right? So the idea is, if you think about the numbers that can divide 30, we call those factors. And so the numbers that can divide both 30 and 18 would be common factors. They would have it in common. They can divide both of these numbers. So 6 is the biggest number, or the greatest number, that can divide both 30 and 18. All right, and the way that you can kind of prove that is by doing what we're going to do in number 2 and number 3, which is we're going to find all of the factors of the numbers and then figure out which ones the biggest are. So number 2 says find all of the factors. Okay, that's going to be a key term that you're going to see in your lesson summary below. Okay, so we can have it down there. All of the factors of 21 and 6. And then from there, we're going to figure out the biggest or the greatest one. So we're just going to go ahead and we're going to list them. We're going to list the factors of both numbers. So let's start with, I need to go to a little bit smaller font size. All right, so factors of 21. Okay, so the numbers that can divide 21. A good way to start out, just to make sure that you don't miss any, as we mentioned in the last activity, was to start out with 1. Okay, and so the way I'm going to do it, I'm going to say 1, but then I'm going to go and leave a lot of space here. And I'm going to put the number that we would multiply times 1 to get 21, which is, of course, 21. Okay, I'm going to go back and put a comma in here. Now, the reason why I'm leaving this space is because I know that the smallest factor of 1 is 1, and the biggest factor of 1 has to be, the biggest factor of 21, smallest factor of 21 is 1, and the biggest factor of 21 is 21 itself. It's that number. So in the middle here, I'm going to put all the other factors. And if I list them in order from least to greatest, it's going to be much easier to find the greatest here at the end. So for 21, let's see, is 2 a factor of 21? No, it doesn't go evenly. So what about 3? Yes, 3 does go evenly, and it's going to go in 7 times, because 3 times 7 is 21. All right, we can get this a little bit closer. Let's see, what else can go into 21? 1 times 21, 3 times 7. Is there anything else? There is not. So we can go back and we can bring these closer together. These are the factors of 21. And then we need, for 6, I'll just put of 6 here. So again, I'm going to start with 1, put a comma, and then some spaces. And it has to be 6, because 1 times 6 is 6. What else can multiply together to give us 6? 2 can, right? 2 can multiply times 3. Is there anything else? There is not. So those are our lists of factors. And so out of this list here, we want to choose the biggest number that you can see. So what's the biggest number we see in both lists? So I look here, if I look at 21, I see 21 is a big number, but it's not over here. 7 is the next biggest number. It's also not over here. 3 is the next biggest number I see here, and 3 is here, right? 6 is bigger than 3, but 6 isn't over here. So the biggest number that's in both lists has to be 3. So the greatest common factor is 3. All right. So number 3 is asking us to find all the factors of 28 and 12 and then identify the greatest common factor. So same idea. So we're going to follow the same lead here. Make a big text box. Let's change the color this time. Let's use a blue. All right, so factors of, the first number is 28. So let's list those out. So I'm always going to start with 1 and then leave some space, and it has to be the number that we're following the factor, so 28. All right, what else is there? Is 2 a factor? Well, I know that the number 28 is an even number. And so if it's an even number, that means that 2 is a factor. So 2 times what gives you 28? The better you know your multiplication table is, the easier this will be. It's 14. I can remove this space here. So 14. Okay, so let's see what else is going to multiply to give us 28. Well, 3? No, 3 doesn't go into 28 evenly, but 4 does. It's 4 times 7. And as it turns out, that covers all of the factors of 28. All right, so let's go ahead and do the factors of 12, since that's the other number that they gave us. Again, I'm going to start with 1 and the number. 1 times 12 is 12. Okay. Now, as a little hint of a shortcut here, what you can do is you're listing the factors of the smaller number. The biggest factor is 12. Look over here to see if 12 is a factor, because if it is, you're done. But in this case, it's not, so we have to keep going. What else are factors of 12? 12 is an even number, so it's 2 is 2 times 6. That's 12. All right, what else is a factor of 12? 3 is. Yes, 3 times 4, and that is the end of our list of factors for 12. So then we want to go ahead and look at the numbers here and see which one is the biggest. So I like to look at the list of the smaller number, like I said, and 12 wasn't a factor over here. Let's check for 6. Do we see 6 over here? No. What about 4? Yes, it is. 4 is there. So the greatest common factor, I'm going to abbreviate it as GCF, is 4. Okay, so problem number 4. A rectangular bulletin board is 12 inches tall and 27 inches wide. Okay, you may want to draw a picture of this and label it with 12 inches tall and 27 inches wide. It may help you to picture what's happening here. Elena plans to cover it with squares of colored paper that are all the same size. So basically the idea is you're going to have a square. You could do something like this here. A square like that. And then inside of that square is going to be a bunch of other squares that are all the same size covering it up. Okay, so we can close this out and take that away. But that's the idea. Inside that square is going to be other squares covering it up. They all have to be the same size. So, and we also know that all of them have whole number inches for their side lengths. So that makes things a little bit easier because we don't have to worry about fractions or decimals. We know that they're whole number inches for their side lengths. So based off of that, we want to know what is the side length of the largest square that Elena could use to cover the bulletin board completely without gaps and overlaps. Well, what this means is, okay, the side length, if there's going to be no gaps, there's going to be no overlaps, and it's going to cover the entire bulletin board, what that means is whatever the side length is, it has to be able to divide the entire bulletin board, the dimensions of the entire bulletin board, which is 12 inches tall and 27 inches wide. Okay, you're going to have to be able to take how tall it is, and you're going to have an even number of squares that are filling up those 12 inches, so it has to be able to be divided evenly. So 12 divided by something, it's got to go evenly, otherwise you're going to have a problem. It's not going to be all the same sizes. But that's also going to have to apply to how wide it is, 27 inches wide. We're also going to have to be able to divide the width, the 27 inches, by a number and get an even number. So what that is getting at is we want to find a factor of both 12 and 27. And because we want to find the largest size square, that means we want to find the largest or the greatest factor. So what they're getting at is they want us to find the greatest common factor of 12 and 27. So we can kind of follow our lead with the earlier problems here and list the factors of all of them and see which one's the biggest. So factors of 12. So the factors of 12, 1 and 12. And we actually have them up here, right? We might as well just go ahead and copy those. We can go that direction. So 6 and then 4 and then 3 and then 2. And bring it back in. So those are our factors of 12. We can just copy those from before. And then the other one was 27. So for 27, we have 1 and the number, 1 and 27. And what else is there? Let's see, does 2 go to 27? No. 3? Yes. 3 and 9. Now, is there anything else that goes into 27? No, there is not. So these are our factors of the two numbers. So we want to look at it and see what is the greatest number here. So if I look at the smaller number here in 12 and then go to the biggest factor of 12, it's 12. Is 12 a factor of 27? No. Is 6? No. Is 4? Nope. Is 3? Ah, there it is. Right, we can circle this right here because sometimes it may help you to see it that way, right? 3 and 3. Okay, I'll go ahead and circle these other ones as well. 3 and 3, and then if it was 4, so 4 and 4. Okay, you don't have to circle them, but for some people it may help to see them circled so you can make sure it's very clear which one is the greatest or the biggest. So basically, question B, how is the solution to this problem related to the greatest common factor? Well, basically, you had to find the greatest common factor. The side length, what this means also, I should say, is that the side length of each of the squares has to be 3. So it's a 3 by 3 square. So if we were to have that here, let's go ahead and X out of that here. Imagine this square here. It would look like this. It would have, each of the sides would be 3. Okay, and then if you were to do this here, you'd have another square. And so if you think about it, lengthwise or height-wise, you're talking about you would have to have 4 of these, right? You'd have to have 4. And then you would have, each of them would be 3, right? So if you have 3 and 3 and 3 and 3, that would be the 12 inches of height, right? And if you go across, how many would you need if you're going across? Let's imagine here, okay, and we're just going to have to imagine that it's 3 again because they're the same. How many of these would we need to fill 27 inches in width? Well, we would need 9 of them, right? We would need 9 across, and then it would be 3, 3, 3, 9 times. So you'd have 9 across, 4 up and down, and so that's how many squares there would be. So you could use that, of course, to also find how many squares there would be total, right? You'd have 36 total squares. All right.